Hello everyone, this is Bandgar SS working as Assistant Professor at Department of Physics, Sachin College, Nasik. Today we are going to discuss TYBSc Paper 5 Semester 4 Advanced Electronics. Today we are going to discuss Chapter 2 Signal Conditioning using a Operational Amplifier. So starting with a principle of analog signal conditioning, why it is need of analog signal conditioning in a electronic system or device. A signal conditioning refers to operation performed on a signals to convert them to a form suitable for interfacing with other elements in the process control loop. Even in application involving digital processing, some type of analog conditioning is usually required before analog to digital conversion is made. Analog signal conditioning provides the operation necessary to transform a sensor output into a form of necessary to interface with other elements of the process control loop. A sensor measures a variable by converting information about that variable into a dependent signal of either electrical or pneumatic nature. It is possible to categorize signal conditioning into several general types. Now, next concept is the signal level and bias changes. One of the most common type of signal conditioning involves adjusting the level, magnitude and bias zero level. If some voltage representing a process variable, in some cases we need to make a sensor output smaller, which is called attenuation. Some sensor output voltage may vary from 0.2 to 0.6 volt. The sensor output must be connected, perhaps require a voltage that varies from 0 to 5 volt for the same variation of the process variable. The required signal conditioning by first changing the 0 to occur when the sensor output is 0.2 volt. This can be done by simply subtracting 0.2 from the sensor out, which is known as zero shift or bias adjustment. Now a voltage that varies from 0 to 0.4 volt, so need to make the voltage larger. If we multiply the voltage by 12.5, new output will vary from 0 to 5 volt as required. This is called amplification, and 12.5 is called the gain. Gain is less or greater than unity. In designing bias amplifier circuits, we must be concerned with issues such as the frequency response, output impedance and input impedance. Next concept is the linearization. The process control designer has little choice of the characteristics of sensor output versus a process variable. Often the dependence that exists between the input and output is non-linear. Even those devices that are approximately linear may present problems when precise measurement of the variable are required. A specialized analog circuit were devised to linearize signal. A sensor output varied non-linearly with a process variable as shown in figure 1a. A linearization circuit indicated symbolically in figure 1b would ideally be one that conditioned the sensor output so that a voltage was produced which was linear with the process variable as shown in figure 1. Such circuits are difficult to design, usually operate only within narrow limits. A modern approach to this problem is to provide the non-linear signal as input to a computer and perform the linearization using software. Virtually any non-linearity can be handled in this manner and with the speed of modern computers in nearly real time. So that shows all the diagrams and their explanation in this. Next one is the convergence. Signal conditioning is a circuit used to convert one type of electrical variation into another. Mostly sensor resistance change either to a voltage or a current signal. This is generally accomplished by bridges when the fractional resistance change is small, and or by amplifier whose gain varies with resistance. First one is the signal transmission. An important type of conversion is associated with the process control standard of transmitting signal as a 4 to 20 mA current levels required. This converting resistance and voltage levels to an appropriate current level at the transmitting end for converting the current back to voltage at the receiving end. The current transmission is used because such a signal is dependent on off-load variation other than the accidental shunt condition that may draw off some current. Thus voltage to current or current to voltage converters are often required. Next one is the digital interface. The use of computers in process control requires conversion of analog data into a digital format by integrated circuit devices called as analog to digital converter, that is the ADC. Analog signal conversion is usually required to adjust the analog measurement signal to match the input requirements of the ADC. Example of ADC may need voltage that varies between 0 to 5, but the sensors provide a signal that varies from 30 to 80 mV. The signal conversion circuits can be developed to interface the output to the required ADC in. Next one is the filtering and impedance matching. Two other common signal conditioning requirements are filtering and matching impedance. Filtering is used to remove the unwanted signal, that is the electric noise. In many cases, it is necessary to use high pass, low pass and notch filter to eliminate unwanted signals from the loop. Such filtering can be accomplished by passive filter using only resistor, capacitor and inductors, or active filters using gain and feedback. The impedance matching is an important element of signal conditioning when transducer internal impedance or line impedance can cause errors in measurement of a dynamic variable. Both active and passive networks are employed to provide such match. So next concept is the filter. Filter is a circuit which are designed to reject or eliminate unwanted signal frequency and allow only desired frequency. So filter are classified by, first one is the low pass filter, that is the LPF. Second one is the high pass filter, that is the HPF. Next one is the band pass filter, that is the BPF. Next one is the band pass or band reject filter, that is the BRF or BSF. Next is the filter and their ideal and practically characteristics. So low pass filter, this circuit gives maximum constant gain for frequency range from 0 to certain cutoff frequency. For higher cutoff frequency, the cutoff frequency gain of this circuit is very low. So see the ideal and practical response of low pass filter. Next one is the high pass filter. This filter circuit provides maximum constant gain for frequency is equal to cutoff frequency or greater than cutoff frequency. So diagram shows the ideal and practical response of the high pass filter. Next one is the band pass filter. This circuit provides maximum constant gain for range of frequency, and the lower frequency with which of given gain is constant is known as a lower cutoff frequency. For higher frequency up to which a gain is constant is known as upper cutoff frequency. So diagram shows their ideal and practical response of band pass filter. Next one is the band stop or band reject filter. These circuits provide maximum constant gain for all frequency except certain range of frequency are called band stop or reject. It shows their ideal and practical response of the band reject filter or band stop filter. Next concept is the concept of loading. One of the most important concepts in analog signal conditioning is the loading of one circuit by another. This introduces uncertainty in the amplitude of voltage as it passes through a measurement process. If this voltage represents some process variable, then we have to uncertainty in the value of the variable. Qualitatively, loading can be described as follows. Suppose the open circuit output of some element is a voltage, say when the element input is some variable of value x. The element could be a sensor or some other part of the signal conditioning circuit such as a bridge circuit or amplifier. This element could be a sensor or some other part of signal conditioning circuit such a bridge or circuit or amplifier. The quantitatively we can evaluate loading as follows. Thevenin's theorem states that the output terminal of any two terminal elements can be defined as voltage source, that is the Vx, and series with output impedance, that is the concept of loading. Let us assume that is the resistance, output resistance, to make the description easier to follow. This is called the Thevenin's equivalent circuit model of the element in figure 2. Such shows the element model as a voltage Vx and resistance Rx. Suppose load RL is connected across the output of the element as shown. This could be the input resistance of an amplifier. For example, a current will flow, voltage will be dropped across Rx. It is easy to calculate that the loaded output voltage will thus be given by Vy is equal to Vx1 minus Rx upon Rn plus Rx. The voltage that appears across the load is reduced by the voltage dropped across the internal resistor. This equation shows how the effects of loading can be reduced. Clearly, the objective will be to make RL much larger than Rx. That is, RL is greater than Rx. The following example shows how the effects of loading can be compromised our measurements. Next one is the passive circuits. Bridge and divider circuits are two passive techniques that have been extensively used for signal conditioning for many years. Bridge circuits are used primarily as an accurate means of measuring changes in impedance. Such circuits are particularly useful when the fractional changes in impedance are very small. Another common type of passive circuits involved in signal conditioning is for filtering unwanted frequency from the measurement signal. It is quite common in the industrial environment to find signals that possess high and or low frequency noise as well the desired measurement data. For example, a transducer may convert temperature information into a DC voltage proportional to temperature. Because of the even present AC power lines, however, there may be 60 Hz noise voltage impressed on the output that makes determination of the temperature difficult. A passive circuit consisting of a resistor and capacitor often can be used to eliminate both high frequency and low frequency noise without changing the desired signal information. The first one is the divider circuit. The elementary voltage divider as shown in figure R1 and R, that is the VD, can be used to provide a conversion of resistance variation into a voltage variation. The voltage of such divider is given by well-known relationship VD is equal to R2 upon R1 plus R2 into Vs, that is the supply voltage. R1 and R2 divider resistors either or can be sensor whose resistance varies with some measured variable. It is important to consider following issues when using a divider for conversion of resistance to a voltage variation. The variation of Vd with either R1 and R2 is non-linear. That is, even if the resistance varies linearly with the measured variable, the divider voltage will not vary linearly. The effective output impedance of the divider is the parallel combination of R1 and R2. This may not necessarily be high, so loading effects must be considered. In a divider circuit, current flows through both resistors, that is, power will be dissipated by both, including the sensor. The power rating of both the resistor and sensor must be considered. Next one is the bridge circuit are used to convert impedance variation into voltage variation. One of the advantage of the bridge for this task is that it can be designed so the voltage produced varies around 0. This means that amplification can be used to increase the voltage level for increased sensitivity to variation of impedance. Another application of bridge circuits is in the precise static measurement of an impedance. So first one is the WHEATSTONE bridge circuits. So the simplest and most common bridge circuits is the DC WHEATSTONE bridge as shown in figure. The network is used in digital signal conditioning application where a sensor changes resistance with a process variable changes. Many modifications of this basic bridge are employed. Other specification application in figure, the object labeled D is a voltage detector used to compare the potential of points A and B of the network. Most modern application, the detector is very high input impedance differential amplifier. In some cases, highly sensitive galvanometer with a relatively low impedance may be used especially for calibration purposes and spot measurement instrument. For our initial analysis, assume the detector impedance as is infinite, that is a open circuit. In this case, the potential difference del V between points A and B is simply del V is equal to VA minus VB, where A is the potential at point A with respect to C and VB is equal to potential at point B with respect to C. So following diagram shows the construction of a simple WHEATSTONE bridge. The values of V and VB now can be found. Nothing that VA is a just supply voltage V divided by R1 and R2. So VA is equal to V R3 upon R1 into V. Here is a similar fashion VB is divided into voltage. VB is equal to R4 upon R2 plus R4 into V. So that is the equation 2 and 3. So V is a bridge supply voltage. If now combine equation 1, 2 and 3. So voltage difference or voltage offset can be written is del V is equal to R upon R3 upon R1 plus R3 into V minus R4 upon R2 plus R4 into V. And that is the equation 4. Using algebra, the reader can show that the equation reduces to del V is equal to R3 into R1 minus R1 into R4 upon R1 plus R3 into R2 plus R4 into V. The process control application using high input impedance detector. Above equation shows how the difference is potential across the detector is a given function of supply voltage and the values of the resistor. Because a difference appears in the numerator of above equation, it is clear that a particular combination of resistor can be found that will result in zero difference and zero voltage across the detector, that is a null. Obviously, this combination from the examination of above equation is R3 into R2 is equal to R1 into R. Whenever a bridge is assembled and resistors are adjusted for a detector null, the resistor value must satisfy the indicated equality. It does not matter if the supply voltage trips or changes, the null is met. Next one is the galvanometer detector used in a WHEATSTONE bridge. The use of galvanometer as a null detector in the bridge circuit introduced some difference in our calculation because the detector resistance may be low and because we must determine the bridge offset as a current offset. When the bridge is null, equation 6 still define the relationship between the resistor in the bridge arcs. Equation 5 must be modified to allow determination of current drawn by the galvanometer. When null condition is not present, perhaps the easiest way to determine the offset current is first to find the Thevenin's equivalent circuit between points A and B of the bridge as drawn in figure with the detector removed. The Thevenin's voltage is simply the open circuit voltage difference between point A and B of the circuit, but where equation 5 is open circuit voltage. So VTH is equal to R3 into R2 minus R1 into R4 upon R1 plus R3 R2 plus R4 into 2. So that diagram is shows the detector is replaced by a galvanometer. Next means the galvanometer detector is replaced by a Thevenin's resistance is found by the replacing supply voltage by its internal resistance and calculate the resistance between terminal A and B of the network. We may assume that the internal resistance of the supply is negligible compared to the bridge arm resistance. The Thevenin's resistance seen at point A and B of the bridge is RTH is equal to R1 into R3 upon R1 plus R2 plus R2 into R4 upon R2 plus R4. The Thevenin's equivalent circuit for the bridge enables us to easily determine the current through any galvanometer with internal resistance RP as shown in figure. In particular, the offset current is Ig is equal to Vth upon Rth plus Rg. Using this equation in conjunction with equation 6 defines the Wheatstone bridge response whenever a galvanometer null detector is used. So here Vth or Rth is in a series like as the Thevenin's circuits. Next one is the bridge resolution. The resolution of the bridge circuit is a function of the resolution of the detector used to determine the bridge offset, thus referring to the case where a voltage offset occurs. When define the resolution in resistance as the resistance change in one arm of the bridge that occurs or causes an offset voltage that is equal to the resolution of the detector. If detector can measure a change of this sets a limit on the minimum measurable resistance change in the bridge using this detector. In general, once given the detector resolution, we may use equation 6 to find the change in resistance that causes this offset. Now, next concept is the lead compensation. In many process control applications, this circuit may be located at considerable distance from the sensor whose resistance changes are to be measured. In such cases, the remaining fixed bridge arm resistors can be chosen to account for the resistance of leads required to connect the bridge to the sensor. Furthermore, any measurement of resistance can be adjusted for lead resistance to determine the actual resistance. Another problem exists that is not so easily handled. However, there are many effects that can change the resistance of long lead wires on a transient basis, such as the frequency, temperature, trace, and chemical vapor. Such changes will show up as a bridge offset and be interpreted as changes in the sensor output. This problem is reduced using lead compensation, where any changes in lead resistance are introduced equally into both arms of the bridge circuit, thus causing no effective change in bridge offset. Now, lead compensation as shown in figure. Here we see that which assumed to be the sensor has to be removed to a remote location with lead wires 1, 2, 3. The wire 3 is power lead, has no influence of the bridge balance condition. If wire 2 changes in resistance because of spurious impedance, it produces this change into the leg of the bridge. Wire 1 is exposed to the same environment and changed by the same amount but is in the leg of the bridge. For remote sensor application, this compensation system is used to avoid errors from lead resistors. Effectively, both and are identically changed. Thus, equation 8 shows that no change in the bridge null occurs. These types of compensation often employed where bridge circuit must be used with long leads to the active elements of the bridge. So, following diagram shows how to keep Wheatstone bridge using a lead compensation. Now, next one is the current balance bridge. One disadvantage of the simple Wheatstone bridge is the need to obtain null by variation of resistor in the bridge. In the past, many process control applications used a feedback system in which the bridge offset voltage was amplified and used to drive a motor whose shaft altered a variable resistor to re-null the breach. Such a system does not suit the modern technology of electronic processing because it is not very fast, is subject to wear and generates electronic noise. A technique that provides for an electronic nulling of the breach that uses only fixed register except as they may required for calibration can be used with breach. The method uses of a current to null the breach. A closed-loop system can even be constructed that provides the breach with a self-nulling ability. This basic principle of the current balance breach as shown in figure. The standard WHEATSTONE breach is modified by splitting one arm register into 4 and 5, R4 and R5. A current I is fed into the breach through the junction R4 and R5 as shown. We now stipulate that the size of the breach register is such that the current flow predominantly through R5. This can be provided for by any of several requirements. The least restrictive is to require R5 is greater than R5. Often if a high impedance null detector is used, the restriction of above equation becomes R2 plus R4 is greater than R5. Assuming that either condition of equation 10 and 11 is satisfied, the voltage at point B is the sum of the divided supply voltage plus the voltage dropped across from the current I. VB is equal to R5 plus R4 upon R2 R4 plus R5 into V plus IR5. The voltage of point is still given by equation 1. Thus the breach offset voltage is given by del V is equal to VA minus VB. So del V is equal to V R3 upon R1 plus R3 minus V bracket R4 plus R5 upon R2 R4 plus R5 minus IR5. This equation shows that the null is reached by adjusting the magnitude and properly of the current I until IR5 is equal to the voltage difference of the first two arms. If one of the breach register changes, the breach can be re-nulled by the change in current. In this manner, the breach is electronically nulled from any convenient current source. In most applications, the breach is nulled at some nominal set of resistors with zero current. Changes of a breach register are detected as a breach offset signal that is used to provide the re-nulling current. A breach circuit is also useful to measure small potential at a very high impedance using either a conventional WHEATSTONE breach or a current balance breach. This type of measurement is performed by placing the potential to be measured in series with a detector as shown in figure. The null detector responds to the potential between point C and B. In this case is given by equation 12 and Vc equal to Vx plus Va, that is the equation by 4. The whereas Va is given by equation 2, Vx is the potential to be measured, the voltage appearing across the null detector del V is equal to Vc minus Vb is equal to Vx plus Va minus V. The null detection is established way. Furthermore, no current flows through the unknown potential when such a null is found. Thus, Vx can be measured by varying the breach register to provide a null with Vx in the circuit and solving for Vx using the null condition. Vx plus VR3 upon R1 plus R3 minus VR4 upon R2 plus R4 is equal to 0. The current balance breach of figure can also be used for potential measurement with no current through the potential to be measured. Here again the potential is placed in series with the detector and is del V defined exactly as a V. Now however Vb is given by equation 12, so the null condition becomes Vx plus Vr3 upon R1 plus R3 minus Vr plus R4 plus R5 upon R2 R4 plus R5 minus IR5 is equal to 0. If the fixed register are chosen to null the breach with I is equal to 0 when Vx is equal to 0, Then the two middle terms in equation 17 cancel, leaving very simple relationship between and the null in current. Vx is minus IR5 is equal to 0. So that is the shows the diagram of potential measurement using bridges. Now next concept, the AC bridges. The bridge concept described in this section can be applied to the matching of impedance in general as well as to resistance. In this case, bridge represented as in figure employs as an AC excitation, usually a sine wave voltage. The analysis of bridge behavior is basically same as in the previous two, but impedance is replaced by resistance. The bridge offset voltage is then represented del E is equal to E Z2 into Z3 minus Z1 into Z upon Z1 plus Z3 into Z2 plus Z. So del is the AC offset voltage. Del is equal to AC offset voltage is the sine wave excitation voltage. Z1, Z2 and Z3, that is the bridge impedance. Null detection is defined as before by zero offset voltage del is equal to 0 from equation 18. This condition is met if the impedance satisfies the relation Z2 into Z3 is equal to Z1 into Z4. This condition analogs to equation 6 for resistive bridges. A special note is necessary concerning the achievement of a null in AC bridges. In some cases, the null detection system is phase sensitive with respect to the bridge excitation signal. In these instances, it is necessary to provide a null of both the in phase and quadrature 90 out of phase as signal before equation 19 applies. So that following diagram shows how to implement AC bridges. Now next concept is the RC filter. To eliminate unwanted noise signal from measurement, it is often necessary to use circuit that block certain frequency and band of frequency. This is called as a filter. A simple RC filter can be constructed from a single resistor and a single capacitor. So first one is the RC low pass filter, that is LPF, RC high pass filter HPF, RC band pass filter BPF, and RC band stop and band reject filter. So first one is the low pass RC filter. It is called as a low pass because it blocks the high frequency passes the low frequency. It would be a most desirable if low pass filter had a characteristic such that all signals with frequency above some critical value are simply rejected. The critical frequency is that frequency for which the ratio of the output to the input voltage is approximately 0.700. Fc is equal to 1 upon 2 pi r. The output to input voltage ratio for any signal frequency can be determined graphically from figure or can be computed V out upon Dn, that is the gain is equal to 1 upon 1 plus f upon fc square, that is the square. So frequency response curve and their circuit diagram, that is the only input resistance. After a resistance we have a capacitor. Next one is the high pass filter. High pass filter passes high frequency, no rejection, blocks reject, low frequency. The critical frequency is defined by the same value as the fc is equal to 1 upon 2 pi rc for the low pass filter. The magnitude of V out upon V is equal to 0.707 when the frequency is equal to the critical frequency. The ratio of output voltage to the input voltage as a function of the frequency for the high pass filter is found to be V out upon V is equal to f upon fc is equal to square root of 1 plus f upon fc square. So the diagram shows the frequency response and their circuit. Next one is the band pass filter. There is the combination of two RC filter. It blocks the frequency below and low limit, and above is a high limit. When passing frequency between the limits, they are known as a band pass filter. The lower critical frequency FL defines the frequency below which the ratio of V out upon V is equal to 3 dB, 0.707. FL is equal to 1 upon 2 pi RHCH. The higher critical frequency FH defines the frequency above which the ratio of V out upon V is equal to 3 dB, 0.707. FH is equal to 1 upon 2 pi RL upon RL into CH. The frequency range between FH and FL is known the pass band. F is equal to FH minus FL. The ratio of the magnitude of output voltage to the input voltage For this filter, as a function of frequency, layout upon V is equal to fH into f upon square root of f square minus fH into fl bracket square plus fl plus 1 plus r bracket complete fH bracket square into f square. So that diagram shows the circuit diagram and their frequency response curve of band pass filter. Next one is the band reject filter. Another kind of filter, some importance is one that blocks a specified range of frequency. Often such filter is used to reject a particular frequency or a small range of frequencies that are interfacing with a digital signal, that the defines are much the same as the band pass filter, in that is a critical frequency above which the signal is attenuated by 3 dB or 0.707, whereas the critical frequency below which signals are attenuated by 3 dB or 0.707. A filter shows that a middle band of frequency are rejected. F is equal to fH minus f1. That is the frequency response of curve, band stop or band reject filter. Next one is the notch filter. It is the combination of 3 RC. It is attenuate the very sharp or the single frequency. One very special band reject filter which can be realized with RC combination is known as the notch filter, because it blocks a very narrow range of frequency. This circuit is known as the ATLT filter. These characteristics of this filter can be determined strongly by the value of grounding resistor and capacitor labeled by R1 and C1 in figure. For the particular combination of R1 is equal to pi R by and C1 is equal to 10 C by pi. The filter response versus frequency R response is given in figure. The critical notch frequency occurs at the frequency is given by Fn is equal to 0.785 Fc, where Fc is equal to 1 upon 2 pi Rs. The frequency for which the output is down 3 dB or 0.707 from the pass band is given by Fn is equal to 0.187 Fc and Fh is equal to 4.57 Fc. So this diagram shows the circuit diagram and frequency response of a notch filter. Next one is the operational amplifier. Most of the electronic equipment required to amplify weak signal. That's why we require a signal conditioning and processing circuit as amplifier. The operational amplifier is widely used in a signal conditioning and processing circuit. The operational amplifier have many characteristics and advantages. First one, very high gain, very high input impedance, low output impedance, negative feedback, infinite bandwidth, infinite CMRR, zero offset, negative feedback, infinite slew rate, infinite SSRR. So that diagram shows their symbol and their relationship between input and output. Op-amp is a circuit composed of resistor, transistor, diodes and capacitor. It typically requires connection of bipolar power supply, that is the plus Vs and minus Vr with respect to ground. One input is labeled with the minus sign, I is called the inverting, and another label with a plus sign is called as a non-inverting input. First one is the ideal inverting amplifier. The op-amp circuit resistor is used to feedback to the output to the inverting input of the op-amp, and R1 connects the input voltage Vn to the same input. The common connection is called the summing point with feedback. The output adjusts to a voltage such that the summing point voltage is 0. No current flows through the op-amp input terminals because of the assumed infinite impedance. The summing point current must be 0. I1 plus I2 is equal to 0, where I1 and I2 current through the resistor R1 and R2. By Ohm's law, we have V in upon R1 plus V out upon R2 is equal to 0. From the above equation, the circuit responses as V out is equal to minus R2 upon R1 into V in. The inverting amplifier gain R2 upon R1, that is shifted in phase 180 degree inverted from the input. The device is also an attenuator virtue of making R2 is less than. Next one is the specification of op-amp. These characteristics are given the specification of particular op-amps together. First one is the input offset voltage. The op-amp output voltage may not be 0 when the voltage across the input is 0. The voltage must be applied across the input terminals to drive the output to 0 is the input offset voltage. Input offset current, a voltage offset may be required across the input to 0 the output voltage. So a net current may be required between the inputs to zero the output voltage. Such a current is referred to as an offset current. This is taken as the difference of the two input currents. Input bias current, this is the average of the two input currents required to drive the output voltage to zero. Slew rate, if the voltage is suddenly applied to the input of an op-amp, the output will saturate to the max. For a step input, the slew rate is the rate at which output changes to the saturation value. This is typically expressed as volt per microsecond. Unity gain, frequency bandwidth. The frequency response of op-amp is typically defined by a plot of open voltage gain versus frequency. Such a plot is very important for the design of circuit that deal with AC signal. It is beyond the scope of this book to consider the details of design employing board plots. Next one is the voltage follower. Shows the diagram directly generated to the output. The input impedance of the op-amp can be greater than 100 megaohm. The output voltage tracks the input over a range defined by the plus minus saturation voltage. Current output is limited to the short circuit current of the op-amp, and output impedance is typically much less than 100 ohm. An op-amp voltage follower whose feedback is provided internally for very high input impedance. The unity gain voltage follower is an impedance transformer in the sense of converting a voltage at high impedance to the same voltage at low impedance. V0 is equal to Vn. The voltage follower buffer has an output that exactly mirrors the input. Next one is the summing amplifier. We given to the two input at the one same input inverting terminal. A common modification of the inverting amplifier is an amplifier that sum or adds two or more applied voltage. The summing point current must be 0. I1 plus I2 is equal to 0 where I1 and I2 current through the resistor R1 and R2. By Ohm's law, the summing 2 points input voltage are V out is equal to minus R2 upon R1 into V plus R2 upon R3 into V. The sum can be held by the proper selection of resistor. For example, we make the R1, R2 and R3. Then output voltage is simply the inverted sum of V1 and V2. The average can be found by making R1 is equal to R3 and R2 is equal to R1 upon R2. Next one is the non-inverting amplifier. A non-inverting amplifier can be constructed from a op-amp as shown in the figure. The gain of this circuit is found by summing the current at the summing point S and using the fact that the sum point voltage is V in, so that the no voltage difference appear across the input terminal. The summing point current must be 0. I1 plus I2 is equal to 0 where I1 and I2 current through a resistors R1 and R2. By Ohm's law, the summing 2 points voltage V in upon R1 plus V in minus V out upon R2 is equal to 0. Solving this equation for V out is equal to 1 plus R2 upon R1 into V in. This equation shows that the non-inverting amplifier has gain that depends on the ratio of feedback resistor R2 and ground resistor R1, but this gain can never be used for voltage attenuation because the ratio is added to the 1. Next one is the differential amplifier. The ideal differential amplifier provides an output voltage with respect to ground that is a sum gain times the difference between two input voltage, where AA is the differential gain. Both V and VB are voltages with respect to ground. Such as an amplifier plays an important role in instrumentation and measurement. V out is equal to VA into bracket V minus VB. The circuits uses two pairs matched resistors R1 and R2. When the matching is perfect, the op-amp is ideal. The transfer function for the amplifier is given by VA out is equal to R2 upon R1 in bracket V2 minus V1. If the resistors are not matched, then CM are poor, input impedance low, not same two inputs, so voltage follower are often used on the input to the provide high input impedance. This is known as the instrumentation amplifier. So see the differential amplifier and instrumentation amplifier using a voltage follower circuit like as a differential amplifier. Next one is the instrumentation amplifier are very high CMRR, common mode rejection ratio, high input low output impedance, very high gain with high stability, very low DC offset and drifts, low noise. Instrumentation amplifier is combination of three op-amps that are into two stages. First stages are op-amps in non-inverting amplifier. Second stage is differential amplifier that may or may not have unity gain. This is circuits allow selection of gains within the certain limits by adjusting of a single register RG. It can be shown that CMR, these circuits, although still dependent on the careful matching of the differential amplifier register, does not depend on matching of the two R1s. The transfer function of this amplifier is given by V out is equal to 1 plus 2 R1 upon RG into R3 upon R2 in bracket V2 minus V. So that diagram shows the instrumentation amplifier, first two amplifiers non-inverting from RG, and next third op-amp is act as a differential amplifier and give the desired output. Next one is the voltage to current converter. It is often used in a process controller, most often transmitted as a current for 220 mA. It must be capable of sinking a current into a number of different loads without changing the voltage to current transfer characteristics. An op-amp circuit that provides the relationship between current and voltage given by I is equal to minus R2 upon R1 plus R3 into Vin. The resistance are R1 in bracket R3 plus R5 is equal to R2 into R4. The circuit can deliver a current in either direction as required as a specific application. When the op-amp output voltage saturates the maximum load resistance and maximum currents are related back, the equation shows that the maximum load resistance is always less than V saturation by R. So RML is equal to R4 plus R5 bracket V saturation upon I minus R3 upon R2 plus R4 plus R5. RML is the maximum load resistance. Vsat is the op-amp saturation on voltage. Rm is the maximum current. So that diagram shows how to convert voltage to convert current by using op-amp. Next one is the current to voltage converter. So that diagram shows how to convert the current into voltage by using op-amp. At the receiving end of the process control signal transmission, we often need to convert the current back into the voltage. This can be done most easily with the current circuit as shown in figure. The circuit provides an output voltage given by V out is equal to minus IR. The current to voltage converter using an op-amp. Care must be taken that the current output capability of the op-amp is not exceeded, provided the op-amp saturation voltage has not been reached. The resistor R in the non-inverting terminal is employed to provide temperature stability to the configuration. Next one is the integrator. Given circuit as an integrator which consists of input resistor, feedback capacitor, the summing point current must be 0. I1 plus I2 is equal to 0, where I1 and I2 current to a R1 and R2. By Ohm's law, the summing two input voltages Vin upon R plus C dV out upon dt is equal to 0, which can be solved by integrating both the terms so that the circuit's response is V out is equal to minus 1 upon RC integration of V and dt. The output voltage varies as an integral of the input voltage with the scale factor of minus 1 upon RC. This circuit is employed in many cases where integration of transducer output is desired. Next one is the differentiator, an op-amp circuit with an output proportional to the derivative of the input voltage. An op-amp circuit has a differential which consists of input capacitor and feedback resistor. The summing point current must be 0. I1 plus I2 is equal to 0, where I1 and I2 current to R1 and R2. By Ohm's law, the summing to input voltage C dV in upon dt plus V out upon R is equal to 0. Solving for the output voltage shows that the circuit response is V out is equal to minus RC dV in upon dt. The output voltage varies the derivative of the input voltage. Next one is the linearization. The op-amp can be linearization, which is achieved by placing the non-linear element in the feedback loop of the op-amp. Summation of currents provides V in upon R plus I V out is equal to 0, where R is equal to input resistor, mu is equal to input voltage, I V out is equal to nonlinear variation of current with voltage. If equation is solved, V out is equal to G into VN upon R, where V out is equal to output voltage G into VN upon R, a nonlinear function of the input voltage. Actually, the inverse function of I V out. A non-linear amplifier uses a non-linear feedback. Next one is the logarithmic amplifier. Here we have to use a feedback as a diode. A diode is the feedback as a non-linear element produce the logarithmic amplifier. If diode is placed in the feedback, then the function IV out is exponential. IV out is equal to I0 exponential alpha V out, where I0 is the amplitude constant, alpha is the exponential constant. The inverse of this is a logarithmic, and thus equation becomes V out is equal to 1 upon alpha log C V in minus 1 upon alpha log E I0R. Thus, the constitute a logarithmic amplifier. Different feedback devices can be produced as amplifier that only the smooth out nonlinear variation or provide specified operations such as the logarithmic. So, I diagram shows how to generates a logarithmic amplifier by using a op amp. Thank you.